Hello, and welcome to the TI Precision Lab introducing SAR ADC input types. In this video, we will look at the difference between single-ended, pseudo-differential, fully differential, and true differential inputs. We will also discuss unipolar versus bipolar inputs. Furthermore, we will explain the difference between a switched capacitor input SAR and a SAR with an internal buffer. This slide shows two very common input configurations for SAR data converters, single-ended and pseudo-differential. The single-ended input measures an input signal with respect to ground. In the case shown, the input is applied to ANP and ANM is a ground sense. Sometimes the ground sense is internally connected and only one input pin will be available. Note that the ground sense has a very limited range. Typically, the ground sense can be at plus or minus 100 millivolts. The graph at the bottom shows how the input is calculated relative to the ground sense. So, if there is a small error signal on the ground pin, it will be corrected for. The pseudo-differential input measures the input signal with respect to 1/2 of the full-scale range. In the example shown, the full-scale range is 3 volts, so the negative input will be connected to half the full-scale range, or 1.5 volts plus or minus 100 millivolts. The voltage connected to the negative input needs to be accurate because the specifications typically allow only plus or minus 100 millivolts of error. The positive input can swing above and below the negative input, producing a positive and negative differential input. In this example, when A and P is at 3 volts, the differential input is 3 volts minus 1.5 volts, which equals 1.5 volts. On the other hand, when A and P is at 0 volts, the differential input is 0 volts minus 1.5 volts, which equals negative 1.5 volts. Thus, for pseudo-differential devices, the output code will be a signed binary number because the differential input can be either positive or negative. Whereas, for single-ended devices, the output code will be an unsigned binary number because the differential input is always positive. The next two ADC input types use differential input signals. Before discussing these types, let's briefly discuss differential signals. The differential input voltage is calculated using the equation VDIF is equal to ANP minus ANM. So for example, if ANP is 5 volts and ANM is 0 volts, then the differential input voltage is 5 volts minus 0 volts or positive 5 volts differential. On the other hand, if ANP equals 0 volts and ANM equals 5 volts, then the differential voltage is 0 volts minus 5 volts or negative 5 volts differential. Even though the input range of each input is 0 to 5 volts, the differential input range is plus or minus 5 volts. In general, the differential input will be double the input range of each input. Another important concept for this type of signal is the common mode voltage. Common mode voltage is defined as the average voltage applied to both inputs. To calculate common mode voltage, simply add the voltage on each input and divide by 2. We will see that the common mode voltage range limitation is an important specification for data converters. The fully differential input is used on many precision SAR ADCs. In this case, the input voltage is calculated using the equation V in diff equals ANP minus ANM, and the differential input range is double the range of each input, as was mentioned on the previous slide. In this example, each input allows signals from 0 to 5 volts, but the differential range is plus or minus 5 volts or 10 volts peak to peak. It is important to realize that the common mode voltage must be held constant at half of the full-scale input range. Maintaining good accuracy on the common mode signal is important because the common mode input specifications typically allow only plus or minus 100 millivolts of error. Looking at the input signal for a fully differential input, you notice that the signal is always symmetrical about the common mode voltage. In this example, the common mode voltage is held constant at 2.5 volts, and you can see that the input signal is symmetrical about this level. Later in this presentation, we will discuss some amplifier circuits that can be used to convert single-ended signals to fully differential signals. This slide covers the true differential input. This ADC input type is very similar to fully differential. The main difference is that a true differential device allows for any common mode voltage within the input range, whereas the fully differential input requires the common mode to be held constant at half of the VREF voltage. In the example shown here, the two inputs can move independently of each other, and the input voltage is calculated as ANP minus ANM. Notice that the common mode moves across the entire input range. Also, notice that the input signal does not have to be symmetrical as it was in the fully differential example. It is important to note that the fully differential input type is the most common. The ADS-8881 was the first true differential input device that TI released. This table gives a summary of the ADC input types. It assumes a 16-bit ADC and uses a 5-volt reference voltage for easy comparison between the input types. This table will quickly allow you to compare and contrast the input pin voltage ranges, the common mode voltage ranges, the full-scale range, and the output code ranges. Since we already covered each topology, we will leave this table for your reference later. Another important aspect of SAR ADC inputs is unipolar versus bipolar inputs. Unipolar inputs accept only positive signals, and bipolar inputs accept both positive and negative inputs. The important thing to understand here is that the polarity of the input is with respect to ground. In the next slide, we will see how a unipolar differential input voltage can be negative, even though neither input is actually negative with respect to ground. When looking at a differential input ADC, you might assume that the ADC is bipolar because the differential input range includes negative and positive input signals. This is not necessarily true though, because a bipolar or unipolar device is determined by looking at the input signal with respect to ground, not the differential input signal range. The example shown here shows how a unipolar ADC with a differential input can have both positive and negative differential signals, even though both inputs are always above ground. The figure on the left-hand side illustrates a negative full-scale input for the ADS-8881. The differential input is always calculated by taking ANP minus ANM. In this example, ANP equals 0 volts and ANM equals 5 volts, so the difference is negative 5 volts. Notice that although the differential input is negative, neither of the inputs are negative with respect to ground. Thus, this is still a unipolar signal because the inputs are positive with respect to ground. On the right-hand side, you can see how applying a 5-volt signal to ANP and 0 volts to ANM generates a positive 5-volt differential input signal. Note that the total input range is from negative 5 volts to positive 5 volts. You can see the transfer function at the right has a plus or minus 5 volt range, but is still unipolar because the ADC does not allow negative inputs with respect to ground. We will now discuss a few common internal architectures of SAR ADCs. There are two major categories of input impedance types: resistive versus switched capacitor. The switched capacitor input uses a sample and hold circuit consisting of S1 and CSH to capture the input signal before each conversion. Normally, the time that the sample and hold switch is closed is very short, for example 300 nanoseconds. Normally, an external wide bandwidth amplifier is required to allow the input signal to settle to the appropriate accuracy within the acquisition period. In this example, a 20 MHz amplifier is required for good settling. Also, Note that this type of converter has a dynamic input impedance, as the input impedance is an RC circuit and not a fixed resistor. Finally, the input voltage range for the switched capacitor input type SAR is normally equal to the reference voltage. Choosing an amplifier and external RC circuit to drive the data converter is a challenging problem. In another video, we will investigate this challenge in great detail. The resistive high-voltage PGA input type SAR has a buffer amplifier or programmable amplifier inside the device. Frequently, this amplifier is in a differential amplifier configuration so that the input impedance of the converter is equal to the input resistor in the difference amplifier. In the example above, you can see that the input impedance is equal to 1 megaohm. This type of input has a very important advantage over the switched capacitor input SAR in that the internal ADC drive buffer eliminates the requirement for an external high-speed amplifier. Another advantage of this type of converter is that the input voltage range can be significantly larger than the reference voltage. In this example, the converter can achieve a plus or minus 12.288 volt input range with only a 4.096 volt reference. Finally, these types of converters tend to have additional integrated features, such as internal references. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content.